Okay, so we are starting a new chapter, and this chapter is going to be all about congruence. We're going to be concentrating on triangles and determining whether triangles are congruent, but a lot of the ideas that we're going to be talking about could apply to other shapes as well, quadrilaterals, pentagons, and other kinds of polygons. So we've talked about this word congruent before. We've talked about congruent angles that have the same measure, and we've talked about congruent segments that have the same length. But now we're going to be talking about entire figures that are congruent. And the basic idea here is that when figures have the same size and the same shape, that's what we mean when we say that those figures are congruent. So another way to think of it, kind of coming off of our last chapter, is that if I can take one figure and perform some kind of rigid motion, or maybe a series of rigid motions, that takes that figure and it maps it onto the other one. So it takes, let's say this black triangle here, does something to it so that it ends up overlapping perfectly, laying perfectly on top of this red one, then we can say that these two shapes are congruent. So that's another way to think about it. If we can either think that they have the same size and the same shape, or we can think that we can perform some rigid motions, reflections, translations, and rotations, that would turn this shape basically into this shape, make them lay right on top of each other. And you can see this example right here. They're telling you, hey, these two things are congruent. We can say that triangle ABC is congruent to triangle DEF, because if I just reflect triangle ABC across this line right here, then what would happen is A would end up right on top of D, C would end up right on top of F, and B would end up right on top of E. And the two triangles then would kind of just lay right on top of each other. And so we could say that one could be mapped onto the other with a rigid motion. So we would say that these two triangles are congruent. Now you'll notice this right here. This is called a congruence statement. Triangle ABC is congruent to triangle DEF. That's called a congruent statement. And it does a couple things. First of all, it tells us that the two shapes are congruent. They're the same size and shape, that we can map one onto the other with a rigid motion. But it also tells us which parts would map to which other parts when we did that rigid motion. For instance, I noticed that the A and the D are both the first point listed in these triangles' names. And that's because that when I flipped the black triangle, when I reflected it across line M, A would end up right on top of D. And then B and E are both the second letters because B would end up in the same location as E when I reflected it over. And C and F, the same thing is going to happen there. So that thing there is called a congruent statement. It tells you that the two triangles are congruent, but it also tells you what parts would match up when we performed the rigid motion to map one figure onto the other. A would match with D, B would match with E, and C would match with F. So in this first example, we're going to try and put some of those ideas that we just talked about to use. It says that given triangle XYZ is congruent to triangle ABC, what composition of rigid motions maps triangle XYZ to triangle ABC? And again, this statement here is giving us some clues that we need X and A to end up matched up. So I need A to end up exactly where X is. I need Y to end up where B is. Y needs to end up where B is. And I need Z to end up with where C is. This needs to end up there. So the question is, how do I perform some reflections, some translations, or some rotations to make that end up happening? So the first thing I'm going to notice here is that my shape XY, my triangle XYZ, it's not facing in the same direction as triangle ABC. So I can't just translate it, because when I just translate objects, their orientation doesn't change. They don't change the way they're facing. In fact, I noticed that in triangle ABC, A is above B. So I would need X to be above Y, because X and Y match up with A and B respectively. So if A is above B, then X needs to be above Y, but down here X is below Y. So I know I need to flip this thing kind of top to bottom. So right away I'm thinking, all right, I want to flip this over some kind of horizontal line here. So I'm going to sketch out a possible line that I'm going to flip this over. I'm going to flip this maybe over this line right here. And what that would do, it would take x and put it above y. But then also I noticed that c is to the left of a. So c is to the left of a, which would tell me I need z to be to the left of x, but right now z is to the right of x. So that tells me I'm also going to need this to be flipped from left to right. So when I flip something left to right, that means I'm going to flip it along a vertical line. So I'm also, once I flip it over this yellow line, I'm going to flip over maybe a vertical line that goes right through here. And then that should get it at least facing in the same direction as this one, which would mean that we could probably then think about translating it. So let's do some of those rigid motions. Let's start by flipping my shape across this yellow line. So I'm going to draw my new shape in this kind of pinkish color, and I see that x right now is 1 unit below the yellow line. So my new location for x is going to be right here, which is 1 unit above that yellow line. So x is going to go to right there. Y is going to go from 2 units above the yellow line to being 2 units below. And z is going to flip from 1 unit below the yellow line to 1 unit above. So now after I perform that reflection there, I have this shape. So I'm going to write off to the side here. What I did is I reflected it across, and that line there, it's a horizontal line going through 3 on the y-axis. So that line is called y equals 3. Okay, so I reflected it across y equals 3. Now I'm going to reflect it across, let me grab another color. I'm going to reflect it across this vertical line right here, the line that goes through -4 on the x-axis. So I'm going to take my pink triangle and now flip it across that. So let's get a new color here. Let's grab this kind of purplish color. Okay, so x is going to go from being 2 units to the left of my line of reflection here to being 2 units right. So now x would be basically where z is, right there. And then z is going to switch places with x. So it's going to go from being 2 units to the right of my green line to being 2 units to the left. So now z will be over there. Y is going to be going from 2 units left of the green line over here to 2 units right. So now my shape, my triangle, looks like this. And so you can see we're kind of on our way. Oh, I should write down that translation here. So remember, I do these things kind of in reverse order. So that's why I'm writing that last reflection I did, I'm writing it to the left of the first one I did. I reflected it across the line x equals -4 because the green line is a vertical line going through -4 on the x-axis. So that's an x equals -4. And what we can see now is at least I have my purple triangle facing the same way as this black one here that I'm trying to map it onto. And I have all the points in kind of the right location relative to each other. Y is directly below x, just like B is directly below A. Z is directly to the left, 4 units, in fact, 4 units to the left of x, just like C is 4 units to the left of A. So all the points are in the right spots. Now I just need to move this thing. I need to slide it so that it's laying right on top of here. And the way that's going to happen is this x needs to slide over by this much. So that would be, what, over 7 units in the positive direction because we're moving it to the right. And then it needs to move down by 2 units. So that would be in the negative, that would be a -2 movement in the y direction. So to write out what that translation looks like, I would say it's a translation by 7, -2. Because I'm moving 7 units in the x direction and -2 units in the y direction. Right 7 and down 2. So this would be one possible composition of rigid motions that would map triangle XYZ to triangle ABC. I guess I didn't draw it out here. Let's go ahead and draw how that ends up right there on top with Z being there, X being there, and Y being right there. Now for this problem here, it's showing us 3 different triangles, and we're supposed to figure out, well, which ones of these are congruent? Or in other words, can I get one of these triangles to map itself to another one of the triangles, because if so, that would mean that it's congruent. So let's start by looking at triangle ABC and triangle EFG. I notice that according to what this is saying up here, I might want to try and get C to end up right on top of G, which would be easy. I would just slide until C is on top of G, and that would take a slide of, let's see, there's 5 from C to the y-axis is 5 units, and then from the y-axis to G is another 5 units. So that's a total of 10 units, just sliding it directly to the right. But I noticed that if I did that same thing to B, it would end up at this location right here, not on top of F, where it would need to be. So that's going to tell me right away, I can't map B to F. I can't map triangle ABC to triangle EFG without changing the shape of triangle ABC. I would have to change its shape to get a B to land on top of F and A to land on top of E, because I notice if I move A over by 10 units, it's going to end up right here, not on top of E. So ABC and EFG are not congruent. What about ABC and JKL? Can I get A to go to J, and can I get B to go to K, and C to go to L? And I noticed right away by looking at that, if anything was going to happen that would make those things map to each other, I need to flip triangle ABC. So let's throw a line of reflection on there, and let's do a quick flip across this line. So this line here would be the line of x equals -7. And if I flip this guy across that line, then B would end up right here, C would end up right here, and then A would end up right here. So now my new triangle would look something like this. That's A. And then connect A to C. And I can see that it's now facing in the same direction as triangle JKL. So now, what if I tried to move A to J, let's say? Moving A to J would mean I'd have to slide over by 1, 2, 3, 4, 5, 6, and then down by 3. Move over 6 and down by 3 would get A to be on top of J. Could I move B on top of K by doing that same movement? Over 1, 2, 3, 4, 5, 6, and then down 3. Yep, B ends up on top of K. And how about C on top of L? 1, 2, 3, 4, 5, 6, 1, 2, 3. Yep, C ends up right on top of L. So if I do this translation of over 6 and then down 3, all of these points, oops, I went too far there. Let me just get rid of that. Over 6 and then down 3. And then I go over 6 for C and then down by 3. All of those translations, they're all the same, so I'm moving this shape by right 6 and down 3. And they all the corners of the shape end up right on top of triangle JKL. So that tells me that triangle ABC is congruent to triangle JKL, because I can flip and then translate triangle ABC. I can do 2 rigid motions to triangle ABC, and it ends up mapping itself to triangle JKL. So those are congruent. Now the last thing I would have to check is, what about this one congruent to this one, triangle JKL and triangle EFG? But I don't even really have to bother with that, I don't think, because triangle JKL we already know is the exact same size and shape as triangle ABC. And we already knew that triangle ABC was not the exact same size and shape as triangle EFG, right? They were not congruent. JKL is the same as ABC, so that would tell me that JKL and EFG, those 2 triangles, will not be congruent either. Now in this last example, it's showing us 2 patterns, and it wants to know, are these 2 objects congruent? If they are congruent, describe a composition of rigid motions that maps one to the other. So one of the things I would notice here maybe is that it looks like the 2 objects have a lot of the same shapes within them. Just kind of looking at the graining in a lot of this, I'm imagining this as like a series of blocks set inside this brown square frame, right? And it looks like it's using a lot of the same blocks, right? But they're not exactly in the same locations. But I noticed this one big red block that in this shape is kind of on the right side towards the top. Over here it's towards the bottom, but kind of on the right end of that. So my question is, I wonder if I rotated this by a little bit, would this start to look more like this? So I'm going to take that shape, and I am going to try rotating that. And I'm going to rotate it 1/4 of a turn, which we know is going to be 90 degrees, right? So I rotated this guy 90 degrees. Oh, trying to get it to go where I want it. There we go. I rotated it 90 degrees, and now I can see that all the blocks are in the same location. But it's not mapped to the other one yet because it's off to the side. But if I were to take it and slide it over, now it's unfortunately, let me see if I can make that go to the front. All right. So now I should be able to slide it over, and it's going to end up basically bloop, right on top of the other one. So it says, describe the composition of rigid motions that mapped one to the other. We rotated it by 90 degrees, and then we translated it. It's not on a grid, so I can't say exactly by how much we translate it, but just a general description of what we had to do is we had to rotate it by 90 degrees, and then we had to translate it so that they would be one right on top of the other.